Glucose yields CO2 and water as products. And so when you metabolize glucose, which is C6H12O6, you need a carbohydrate. So you eat the sugar, and then you inhale oxygen, and then you exhale CO2, you produce some water in the process. And so is the sugar burned in your body? In a sense it is. You know, it's completely oxidized. But there's no flame that occurs in your body, right? In fact, in your body, this happens over many, many steps. It's one of these biochemical cycles. But it doesn't matter because we know what the final state is and what the initial state is. It doesn't matter how many steps it takes. Because the sum of these steps will add up to the net energy we're going to get from this. And so to balance this, we'll need 6 oxygens here and 6 CO2s, 6 waters. And so we'll have a delta H for the reaction. And so if I were to burn the sugar, let's say in a coffee cup, versus burn the sugar in your body, would they yield the same amount of heat or different amounts of heat? And it's not just heat. I mean, you know, what we want to do is we don't necessarily want just heat, right? We want to get some probably work out of this. If you're going to burn it in your body, is it just generating heat? No. And so the question is, are you going to get the same amount of energy as if you were to combust this versus metabolize it? So the delta H for this, which is metabolism of glucose, is it the same as delta H of combustion of glucose? What do you think? You would think it'd be different, right? Because I mean, if you metabolize it in your body, it's not like burning it in a cup. But it turns out it's this exact same amount of energy. It's the exact same amount of energy because, you know, delta H is just a state function. It doesn't matter how you get there. It just depends on the final state and the initial state. There's no difference here in the final state and the initial state, other than the temperature, because if you burn it in your body, you know, the temperature is going to be slightly different. You probably versus 298 Kelvin. But we'll assume that difference is slight, you know. But essentially, you're just going to get the same energy. You know, for biochemists, they don't use 298 for their reactions. You know what biochemists use for theirs? If they're looking at their delta H's, they don't use 298 like we use. They typically use body temperature. It turns out, though, that delta H at body temperature and delta H at 298 Kelvin isn't so significantly different. You know, it's a little bit different, but not significantly. There's something else they look at, though, which would have a more significant temperature impact. But for the most part, you know, it's just the same exact amount of energy because it's the same exact reaction. And this is what a state function is. You always want the same amount of energy, you know, given the same initial and the same final state. Okay. So if we metabolize it, heat released in the process. Well, the first thing is, what is delta H? Actually, they don't tell us what delta H is. They tell us this one here, down here. And that is delta H of formation under standard conditions of C6H12O6 solid is minus 1273.3 kilojoules. So what a lot of people will say is, oh, you know, this must be minus 1273.3 kilojoules. Is that correct? No. Is this reaction as written delta H of formation for glucose? No. What is a formation reaction? This is incorrect. But I've given this, you know, problem for people to do, and that's a common mistake. What is a formation reaction defined as? So if I see delta H of formation of C6H12O6, what's the chemical equation I would write for that? Just tell me.
Carbon solid.
Yeah, carbon solid. Which form of solid carbon? Graphite. How many of those would I need? 6 carbon solid graphite plus 6H2 gas plus 3O2 gas yields this. That would be a formation reaction. So why are they giving us delta H of formation here? Well, I kind of get a clue. They're giving us delta H of formation here so we could figure out what delta H of this reaction is using Hess's law with formation reactions. If we use Hess's law with formation reactions, and this is pretty easy. The answer is here is yes, they are equal. Right? And so then we don't have to write out the reactions because all those elements will cancel out. You know, if you're just using formation reactions, then it's not difficult here. And so delta H for the metabolism is equal to delta H of combustion, which is going to equal the sum of mu P delta H of formation of the products minus the sum of mu R delta H of formation standard delta H of formation of the reactants. And so the products, we have 6 moles of CO2, gas. And so we have to flip back to Appendix D. Let's take a look and go to carbons. So there's carbon C. So I look under C here for CO2. I'll see CO2 gas here, minus 393.5. So minus 393.5. Minus 393.5 kilojoules per mole. All right, and then I have 6 moles of H2O. H2O is a liquid, so H is hydrogen. We'll have to go to H. So flip over to H, and then look for H2O. H2O liquid. You got to watch out because there's H2O gas as well. So H2O liquid is minus 285.8. Minus 285.8 joules per mole. Minus the products. So the products, I have 1 mole of glucose. C6H12O6. Solid. Let's say I have glucose is in Appendix D. The organics they list at the end, in organic substances table. We'll go down the list, and actually there is no glucose in Appendix D. And so this is why they gave it in the problem. They gave us the data here. Delta H of formation for glucose is minus 1273.3 kilojoules. So we have 1 mole of glucose times minus 1273.3 kilojoules per mole. And then we have 6 moles of O2 times, what's the delta H of formation for O2? 0. So that drops out. And so we can figure out what the heat of metabolism or the heat of reaction or the heat of combustion is for this. This is all the same. So let's go ahead and calculate that.
I have a question.
Uh-huh.
You did reactants minus products.
Did I do reactants minus product? It should be products minus reactants. Yeah. It's got to be products minus reactants. We've got to watch out for the sign too. 6 times 393.5. $285.8. And it's 1273.3. $2802.5. The sign's very important. Negative 2802.5 kilojoules. That's written. The moles cancel out. This kilojoules for this reaction is written. Now, if it's positive, it's a totally different thing. If it's positive, then this reaction requires energy. And going from reactant to product, but since it's negative, it releases energy. And this energy is just energy. This energy is already factored in for the tax. So we don't, this is the net energy we're going to get out of this reaction. Now this energy is Q, but we can always add more work in there. In fact, we don't want to convert this all to heat. When you consume this sugar, you just don't want just heat. You want energy to do work. And so let's take a look at this. The heat released in the process is converted to useful work with about 70% efficiency. And so what that means is for every 100 joules that I have of net usable energy, the heat, only 70 joules will be converted into work. The other 30 joules will be converted into heat. It's hard to find a mechanical system that will give you 100% work, right? Because even the pulley, what I had drawn with the slide, there's going to be some heat generated by the pulley. I didn't tell you. Maybe I said it's a frictionless pulley. And that's a frictionless slide, but in reality, there's really, it's not going to be a frictionless pulley. And it's not going to be a frictionless slide. There's going to be a slight amount of frictional losses. Even when you walk through air, there's going to be some frictional losses. You can feel the friction of air against your body. And so, so what we're going to do is we're going to say, yeah, it'd be great to convert all this into work. If we could convert all this into work, then we would have 100% efficiency. But we're just going to assume that, in metabolism, we're only going to get about 70% work, 30% will be just left as heat, or converted into heat. All right, then the question is, calculate the mass of glucose metabolized by a 58.0 kilogram person in climbing a mountain. Well, a 58 kilogram person climbing a mountain, how much energy are they going to need for that? Well, it depends on how tall the mountain is. And so the mountain in this case is 1,450 meters tall. And it depends on the path, Is it just straight up, kind of like an elevator, 1,450 meters straight up, right? Or do they, go back and forth, climbing up the mountain? There's going to use different amounts of energy, depending on the path. And so the amount of work to climb the mountain is not a state function. It depends on how difficult the mountain is to climb. And so what they're going to do here is they're going to assume that the work, the minimum amount of work to climb that mountain is if they just got in an elevator and just went straight up. Right. And that elevator would be the minimum. And so what we're going to do is we're going to assume that the work performed in the climb is about 4 times the minimum. The minimum is that required to simply lift 58 kilograms by 1,450 meters, the pulley system. But it's probably going to require more work because you probably have to follow some kind of path to get up the mountain. And so what we're going to do is we're going to multiply that by 4. And so this comes from physics. So this is why I wanted to do this problem, because let's say we're going to climb this mountain here. This mountain is 1,450 meters tall. And this person is 58 kilograms. This is out of scale, of course. 58.0 kilograms. So the minimum is if you just got on an elevator and just pulled the person straight up to the top. If that's the case, then the energy that's required for, we can get from physics. The energy that's required to do this is, let's see, energy, minimum energy, is equal to the mass times the gravity, times the height of the mountain. Because we've got to fight gravity in this case. And so, well, the mass is 58.0 kilograms. Gravity is 9.8 meters per second squared. And the height is 1,450 meters. Oops. And so what are the units for this? Well, that's kilograms meter squared per second squared, which you've heard before, which is what? This is a joule. So let's see how many joules minimum is required to climb this, which would be 58. You don't have to memorize this. This is from physics. Times 9.8 times 1450. And they don't give this. You know where they give this information? Where do they give this? Like, if I didn't explain this, do you know where you would get this type of information? It's actually in our book. Have you ever looked? Most people don't bother looking at the appendices. This is one of the reasons why I want to go back and take a look at the appendices. To use these. We have something called Appendix A, which is a math review. Appendix A. So this is a good place to go to brush up on logarithms, algebraic operations here. It's a quadratic equation. In Chem 1B, we use the quadratic equation quite a lot, and so this is useful to have. But it's not all review, because there's one more method here. This is called, zoom in here. This is called the method of successive approximations. Have you covered it before? The method of successive approximations? So this section is not entirely review. Some of this is totally new. The method of successive approximations. It should be totally new. The method of, have you done the guess and check method? Have you ever heard of that, the guess and check method? The guess and check method is you just keep guessing the answer until you get it right. And so this method of successive approximations is just a fancy name for the guess and check method. And so for example, if I have 2x equals 6, I might guess, I might guess x values. Like say, for example, if I guessed x is 1, then I get 2 is equal to 6. Well, that didn't work. Right? It's too small. I might guess x is 5. If I guess x is 5, then I get 10 is equal to 6. Well, I'm getting farther away on the other side. So it's between 1 and 5. So I'll guess x is equal to 4. And then I'll get 8 is equal to 6. So I'm getting closer. And then finally, I'm going to guess x is equal to 3. And I get, 6 is equal to 6. I got it. Therefore, x is equal to 3. This is the method of successive approximations. You just keep guessing until we get the correct answer. And it proves to be quite useful, especially in Chem 1B. And so there's about a page and a half of that. And then continues on with graphs. Here. Graphs. Oops. You see an example of graph there. Dimensional analysis, although, dimensional analysis is covered in chapter 1. We just give some additional. Levels. And it's not all at the chapter 1 level. Some of this is more complex, like when we have to square it or the cube, the whole thing. And that's it. Appendix B is physics, basics. And so the basics of physics here, pretty much Newton's laws. We have velocity and acceleration, V1. Force is going to be in units of newtons, to kilogram meter per second squared. Work is going to be Newton meters, to be kilogram meter squared per second squared. So force and work. And so from here, we could see that the work is going to end up being mgh. Although it doesn't look like. The work involved in climbing this mountain is the force, mg, times the distance. Well, in this case, the distance is the height. And so it would be mgh. And so Petrucci was expecting you to be able to dig this up, unless you already had some physics. You had some physics then okay. Or you could have figured it out dimensionally. Using dimensional analysis, we know that kilogram meter squared per second squared is a joule. And so just multiplying those things together, we could have gotten it. We have work here. We've got kinetic energy. And then it goes on. We've got magnetism. We've got static electricity. This is an equation I talked about in chapter 1. Do you recognize this equation here? B13. What is that equation? What's the name of that equation? Force is equal to Q1 times Q2 over R squared. There's some constants there. This is Coulomb's law. And so here we get into Coulomb's law. An example here. Current, which we'll talk about in Chem 1B. Electromagnetism, which we don't really talk about much, but it's an important topic. SI units in Appendix C. Here where you can find, if you ever forget the definitions for joule, here you can find the definition of joule, which is kilogram meter squared per second squared. A watt, which is joule per second. A coulomb, which is an amp per second. A pascal, which is Newton per meter. A Newton, kilogram meters per second square. A volt, an ohm, a coulomb, and we'll get into that. This was something I was disappointed to see, though. This is one of my favorite units, the angstrom, which I like a lot. I like angstroms, but when I looked at the heading for this, then I was disappointed because they want to abandon
You want to abandon angstroms. What else do they want to abandon? You see what else they want to abandon that I like quite a lot? Atmospheres. Yeah. Units to be discouraged or abandoned. Okay. Millimeters of mercury, atmospheres. All that stuff you spend lots of time learning probably in Chem 4 is to be discouraged or abandoned. All right, now we're going to Appendix D. So this is where we're at. With Appendix D data, then this is, because Appendix D is pretty comprehensive. There are a lot of things in there, although glucose was missing. And so using Appendix D data, we don't have to do much calorimetry. We can, figure out the delta H's of reaction pretty easily, like this. But how about something like the delta U of reaction? The delta U of reaction. Delta U, Hess's law works for delta U too. Do I have any delta U's of formation in Appendix D? Nah. So if I wanted delta U, let's say, if I metabolize this, metabolism occurs at constant pressure. Or if I combust this, well, I'd combust it at constant pressure. But there is a chance that these aren't equal. That is, if I combusted this, not in the open lab, but if I combusted this in what? There's a chance that these two would not be equal, and that would be in a bomb. If I combusted this in a bomb, they are likely not to be equal. And so, in this case, this is our capstone problem. So I want to talk a little bit about delta U here before we answer the question. And that is, what do you think? If I burn this in a bomb, would I get more energy, less energy, or about the same amount of energy? I get less? How come I would get less energy if I did this in a bomb? The same? How come I'd get the same amount of energy if I did this in a bomb?
There's no work done.
There's no work done? How can you tell there's no work done?
Zero.
Oh, yeah. Yeah, you're absolutely right. There's no work done at constant volume. But this number is not the constant volume number. This number is, what is this number? This number is this is not the constant volume number, this is the constant pressure number. If I had the constant volume number, then that's fine. I'd know, yeah, there's no work done. All that internal energy was converted into heat, of which we can use some for work. But you tell me, what do you think? How do we know when delta U and delta H are less than, greater than, equal to? How do we know? Change in volume, right? A change in volume under, well, you might say, hey, there's no change in volume. Delta U is in a bomb. There's no change in volume. It's change in volume under what conditions? Under constant pressure conditions. So under constant pressure conditions, did we have a change in volume here? Well, there's different levels of detail you look at it. Roughly, we might go something like this. 6 moles of gas is how many liters? 150 liters. 6 moles of gas. 150 liters. And then over here, how many moles of gas do we have? 6 moles. So this is going from 150 liters to 150 liters, then there's no volume change, right? And there's no work. But is that accurate? Not really. It's not that accurate because I'm ignoring what? I'm assuming that the solids are negligible and the liquid is negligible. Is that an okay assumption? What do you think? Is it okay to ignore the solids and liquids? In general, yes, because the change in volume is so small. But even though it's small, I don't know, because you might say, if somebody ever asked you, how much work are you ignoring? Is it really safe to do that? To ignore that little bit of work? And so somebody might ask you one day, how much work is that? And then you might say, really small. And then they might say, how small? And then you say, really small, but I really don't know because somebody just told me to ignore it. And so, based on what they told me to do, I've been ignoring it, but I really don't have any numbers for you. Or do you have some numbers? Well, you know what? Let's do a side. You want to do a side calculation? The amount of work Petrucci's going to tell you is really small. In fact, this is what Petrucci says to do. Have you looked at the homework? If you look at the homework, do you know what Petrucci says to do? This is what Petrucci often says to do. We did 37 earlier, and I didn't talk about this that much then, but xylose. Assume, look at this in parentheses, assume for this reaction that delta U is approximately equal to delta H. Is that a safe assumption? Well, in this case, I don't know. We'd have to justify it in some way. And so we might do the same thing. Well, in number 37, Petrucci is said to assume that delta H and delta U are about the same. So maybe we'll do the exact same thing in this problem, problem number 108. Although we don't care, in 108 to answer this, they aren't asking us about delta U, but I want to talk about delta U right now because we want a bigger picture of what's going on. And so is it okay to say, well, delta U is going to be about 1273.3? Is that safe to say? Delta U and delta H are about the same. Delta H is minus 1273.3. Delta U is minus 1273.3. Yes? Would you feel comfortable doing that? What do you think? Well, you don't know really until you actually do the calculation, so we might as well just do the calculation. What do you think? Should we do it? But you know what? In this case, I'm going to try to go. Oh shoot! I'm going to try to do a more accurate calculation. Petrucci says, well, if you're going to calculate the work, just kind of ignore the solids and the liquids. And then if we do the gases, we're just going to assume that the gases behave ideally. But do you think CO2 and O2 are going to behave equally, ideally? What do you think? What causes a gas to deviate from ideal behavior? Because, so far all we've been doing is assuming just pure ideal behavior. But, if it starts to deviate from ideal behavior, Wouldn't that affect the volume? And it does. It affects the volume, yes. And so maybe, maybe in this case, you know what I'm going to do? I'm not going to assume ideal behavior. I'm going to assume real gas behavior because, I want to minimize the errors in the calculation, and making an assumption that the gas is behaving ideally is an error. Correct? It's an error. And so, I kind of skipped this section in chapter 6 because, when do we apply this equation? And so let's take a look. This equation here. When do we apply equation 6.26? Equation 6.26 is an equation that tries to correct the ideal gas law for real gases. There are two corrections here. Normally the ideal gas law is PV equals nRT. But here there's a pressure correction here. Do you know now what's going to happen is, if there wasn't this pressure correction, the pressure would be larger. But now there's this pressure correction. The bigger this pressure correction is, the lower the pressure actually becomes. And so what is this pressure correction? Well, this pressure correction is n squared. N is the number of moles, and volume squared. And so it's like moles over volume. It's kind of like density in a way. Times A. Now what is A? A is what we call an empirical correction. Empirical correction is they just do some measurements and then they come up with fudge factors, and these fudge factors correct the pressure. And so let's take a look at how A changes. If we look at the table, these are A's, and A's are going to be different depending on the gas. So if you look, hydrogen and helium, actually helium has a very low A. And so if it has a very low A, that means it has a very small correction, and that means helium behaves the most ideally in terms of A. What's the worst? The worst one I see is the worst one looks like propane. Propane has a 9.39 A value. Okay. And so what is A? This is what A is. A is this. The bigger the A, the stronger the intermolecular attractions. The stronger the intermolecular attractions, the weaker it's going to hit the wall. See, if you have these three molecules attracting this one back, then this one's not going to impact the wall with the same force. Versus if the weaker the intermolecular attractions, the stronger this will hit the wall. The stronger this hits the wall, or the more forceful this hits the wall, then the higher the pressure. And so what A is a measure of the intermolecular attractions. And the bigger the intermolecular attractions, the less ideal, the lower the pressure you expect. Right? And so what intermolecular attractions does is it lowers the pressure. Where's CO2? Where's O2? Well, CO2 is about 4. O2 is about 1. And so O2 is kind of getting close to ideal, right? But CO2 is kind of deviating farther from ideal. And that's going to impact pressure. And so both of these, if both of these were helium, then fine. You know, helium's pretty ideal. Don't have to worry too much about it, right? Because the intermolecular attractions are weak. Water is pretty bad, you know, because it has very strong intermolecular attractions. And so the A term is going to be very large. Does that make sense? Okay. And so that's the A term. So CO2 is here. It's got some intermolecular attractions we got to contend with. And so this is called the pressure correction. The other term here is the volume correction. Now, if you have 1 liter of gas, do you have 1 liter of empty space? If you have 1 liter of gas, you don't have 1 liter of empty space, because some of that space is taken up by the molecules themselves. And so the more molecules you have, and the bigger the molecule is, B, then the less empty space you have. And so that 1 liter is not really 1 liter. The 1 liter is going to be less than 1 liter. Does that make sense? Of free volume in which to move. And that's going to impact things. Here. Put this on. And so, let's take a look at the B correction term. If we look at the B correction, the smaller the B, the more ideal it is. You know, for an ideal gas, A and B are both 0. If A and B are both 0, then PV equals nRT. The bigger the B term, the bigger the molecule, and the more the volume screwed up. And so the closer to 0, the better. It looks like helium, again, is the closest to 0. CO2, 0.0429. The highest looks, on this chart, the highest looks to be propane at 0.09. O2 is at 0.03. And so again, CO2 is about midway between helium and propane. Propane is not the least ideal. It's the least ideal on this chart. All right, and so what this means is maybe we shouldn't use the ideal gas law to calculate the volume. Remember, I used the ideal gas law to calculate the volume, molar volume at 1 bar. The molar volume at 1 bar is 24.8 liters per mole, right? I'm not going to use that because that's for an ideal gas. I want to be even more accurate because somebody might confront you and say, are you sure you can use the ideal gas law? Is it okay to use the ideal gas law indiscriminately? CO2, O2? Isn't CO2 less ideal? Yeah, CO2 is less ideal. Well, what kind of error are you introducing by using the ideal gas law? So I think in this case, you know what? In this case, I'm going to go for the real, or the van der Waals equation for real gas. Let's do it. Let's try to be as accurate as possible in our volume calculation, because the volume change is going to be kind of small. Do you see the volume change is going to be kind of small? And so let's try to be accurate in the volume change here. And so let's figure out the volume change here. So can I erase this here? Actually, did I calculate the energy? No? Oh, shoot. I need to calculate the energy. Or can someone calculate the minimum? $824,000. 180. 824,180 joules. Okay. Then they're going to just pick some arbitrary number, 4 times that, and just say, well, it's not going to be the minimum. We're going to expend more than the minimum. How much more than the minimum? Well, we're going to guess 4 times more than the minimum. Does that sound reasonable? Yeah? No? All right, so go ahead and multiply this by 4. So we're going to assume for this specific mountain, 4 times the minimum energy is required. What does it come out to? 3 million? All right, go ahead and give me the full number. 3 million? 296,720 joules. And so we're going to convert this into kilojoules. This would be 3,296.7 kilojoules. That's the amount of energy required. A mole of glucose is not enough. Yeah. Well, let me continue with my side calculation. I don't mean to confuse you too much, but this is like the capstone problem. This is the final problem I want to do. And so we want a clear understanding between delta H and delta U. And so I want to go back to delta U. How can I figure out what delta U is? If, let's say if your stomach was like a stainless steel bomb or something like that, and the volume couldn't expand, it couldn't contract, right? How much energy would you get? You've gotten the same amount of energy? Less or more? And we can figure that out if we know what happens to the volume. Did the volume expand? Did the volume contract? Or the volume stay the same? Looks like it pretty much stays the same, but a small change in volume. And so let's remember these two numbers over here. Let me write these down. Okay, what we say is delta H metabolism for the glucose. This is under standard conditions because appendix D happens to be under standard conditions. And appendix D standard conditions consist of what? 2 things. Standard conditions is for appendix D is 1 bar and 1 molar. But the temperature for appendix D is 25 degrees C, 298 Kelvin. And so because we're using appendix D, it's going to be at 298. But that's not given by this little superscript. Usually, in order to specify the temperature, we have to add it down here. This is at 298.15 or just 298 Kelvin. Just leave it like that. I don't want to write the 0.15 all the time. Because that's not given by this little symbol here. And so we write delta H naught 298. Okay. And that's going to equal minus 2802.5 kilojoules. And then the energy required by the climber. The energy required by the climber is 3296.7 kilojoules. 3,296.7 kilojoules. So, well, you know what I'm going to do? Let's finish this problem because we're just about done with this. And then we're going to go back and look at delta U and delta H. And so this turns into a dimensional analysis problem. The dimensional analysis problem is, what am I given? I'm given I need 3,296.7 kilojoules of energy to climb this mountain. And so this is required. Where's this energy going to come from? That energy is going to come from the glucose. When I look at the glucose metabolism, I can write this as kilojoules or kilojoules per mole of glucose. I'm going to write it kilojoules per mole of glucose. And so I'm going to get minus 2802.5. But there's something else I have to worry about. I have to worry about the efficiency of the metabolism of glucose. And the efficiency is 70%. And so what this means is for every 70 kilojoules of actual usable energy, I need to produce 100 kilojoules. I talked about this earlier, this is like percent yield. If you're baking cookies and you eat 30 of them, and you need 100 of them, then you better bake extra, right? And so this is it. If we need this many kilojoules of energy, then we have to account for the loss. We're going to lose, for every 100 kilojoules of energy we produce from this reaction, we're going to lose 30 of those kilojoules to heat, right? And the other 70 kilojoules will be converted into work of climbing this mountain. Well, that means there are two works for this. What are the two work terms here? And so when I'm thinking about this, this is the way I'm thinking. Delta H is equal to Q, delta U minus the W. Well, in this case, the W is going to take on 2. We got the natural work of the chemical reaction, which is the P delta V work, and the climbing work. And so we got the work of climbing the mountain minus the work of P delta V. And then the rest will be heat. All right, so for every 70 kilojoules net, we have to have this many kilojoules gross. There's going to be some loss. We're going to get that from here. This is going to be minus 2802.5 kilojoules. Now we could do this as system and surroundings. If we do this as system and surroundings, then the work, the work absorbed by the climber is equal to minus the work lost by the surroundings. The surroundings would be the metabolism here. But I'm not going to do that. What I'm going to do is this. I'm going to change this sign. Rather than saying minus 2802.5 kilojoules, I'm going to say 2802.5 kilojoules produced. Or lost. And then I can get rid of that negative sign. Does that make sense? But for calorimetry and other thermodynamics, for calorimetry it's critical. I don't get rid of the negative sign like that. But in this case, the reason I'm going to get rid of it is because if I don't get rid of that, I'm going to get negative grams. Does that make sense? No. It doesn't. And so the way to think about this is whatever energy is lost by metabolizing the sugar is going to be energy absorbed by the climbing. And so I could have set up an equation up here, but I'm not. I'm just going to say per mole of glucose here. Because what's going to happen is this. What's going to happen is you're going to just be given a delta H. The delta H is going to be like this, minus 2802.5, and then it's going to be up to you to determine, how to handle the negative in that case. All right, and then how much does glucose weigh per mole? 180.2 grams per mole, if I recall. but let me double check that. And so 180.2. Well, actually, I don't want to do that. 6 times 1201 plus 1212 plus 6 oxygens. 6 would be 6 is 2, 48, 96. That's 96. 180.18. 180.18. Let's go with 180.18. 180.2 is what was on Wikipedia. I looked at that the other day. So let's see how many grams of glucose. This is 3296.7 times 100 divided by 70 divided by 2802.5 times 180.18. This is equal to 302.79 grams of glucose. So how are you going to get that? Well, this person can consume straight glucose, or they might eat some chocolate bars or candy bars or something like that. If they eat candy bars, does it tell how much glucose is in there? No, you know what it says instead? It says how many grams of carbohydrates in there. But carbohydrate, you know, is that going to be so? We got to know what carbohydrate it is, right? Because glucose is one carbohydrate, sucrose is another carbohydrate. Lactose is another carbohydrate, fructose is another carbohydrate, right? There's fruit sugar. So you've heard of these different carbohydrates, right? And so then I want to know, because I don't want to go and buy, chemical grade glucose. I just want to buy some food, and the food unfortunately doesn't list how many grams of glucose is on there. But you biologists probably know, Do you know the number? Petrucci used to have this number. This is what I was looking at for it in the PowerPoint. Let's take a look at if Petrucci has this. It just didn't put it in the PowerPoint. Fuels as a source of energy. I was going to check this on the internet, but I can't even log onto my computer, onto the computer right now. But here we see the heats of combustion of some fuels per gram, right? But and this is don't quote me on this, but as I recall, there are 11,000 calories per gram of carbohydrate. And so it really, all the carbohydrates have about the same energy per gram, which is about 11,000 calories per gram. Well, 11,000 calories, that's a lot of calories, isn't that? Per gram. And so what food chemists decided to do was, they don't want to talk such big numbers. And so they came up with a new calorie. And so this would be 11 food calories per gram, where one food calorie is 1,000 chemical calories. And so it turns out that carbohydrates and proteins, so if you metabolize a protein, it's like burning protein. So if there's some nitrogen in there and other stuff. Carbohydrates and proteins are about the same yield of energy, about 11 calories per gram. Fats, however, have a little higher yield of energy. Does anybody know the number for fats?
9
Is it 9?
calories?
Yeah.
Yeah.
Fats? Then I have this wrong.
It's proteins with 4.
Yeah, proteins are 4, carbs are 4.
Carbohydrates are 4?
Mhm.
Oh, okay, I have this wrong. My memory isn't so good. 'Cause I don't use this that much. So it would be, I'm sorry, it would be like 4,000 calories, which would give us 4 food calories per gram for carbohydrates and proteins, and fats would be 9 food calories per gram. Is that right? Okay. And so, you know what? If we're going to consume a candy bar here, then we don't really need to know if it's glucose or not. We just, we'll get approximately the same for the carbohydrates. There'll be a slight difference, but approximately the same. Okay, are we good with this? All right. So this would be the conclusion. Some of those calories are wasted. About 30% of the calories are wasted as heat. Well, it's not really wasted as heat because you need heat to keep your body warm too. But 70% of the calories are going to be used for work in climbing the mountain. And so this would be the efficiency of converting the energy to work. 70% converted to work. All right, so we're good with this then? I'm going to go back to the question. If you had like an iron stomach or something like that, like your stomach was a steel bomb, and the volume couldn't expand or contract, would you have gotten the same amount of energy, less energy, or more energy? And so let's go back and answer that question. Although it's not realistic, but if we did it in a constant volume, what would have happened? Now, when we look at this, Petrucci would have said we got the same amount of energy, right? We would have gotten the same amount of energy, but you have to learn in science, in science somebody is going to want numbers. And so if you say, well, it's going to be about the same amount of energy, then they're going to ask you, well, what kind of percentage error are you introducing by ignoring the solid and liquid? And you have to give them a number, like, is it like 1%, a tenth of a percent, a hundredth of a percent? What kind of error are you introducing? And so what we're going to do is we're just going to do one calculation to see what kind of error we're introducing. But we might as well try to go all out. And not only that, we might as well try to go with real gas rather than ideal gas. Because what kind of error are we introducing by assuming that these are ideal gases and not real gases? Right? And so what we're going to do is we're going to do this. We're going to start off here with glucose, C6H12O6 solid, 1 mole, and 6 moles of O2 gas. Now the 6 moles of O2 gas, so the volume initial is equal to the volume of the C6H12O6. Well, the density of glucose doesn't expand like naphthalene. Naphthalene was kind of crazy. As far as glucose is a much more dense solid. And so I don't have the density of glucose memorized. I'm going to look that up right now on my phone since I don't. Glucose density. Let's see if we can get a decent number here. 1.54 grams per cubic centimeter. And so this is going to equal the volume of the glucose plus the volume of the O2. Now the volume of the glucose is, we have 1 mole. 1 mole is 180.18 grams. So 180.18 grams of glucose, which is a mole, times the density of times the inverse of the density, 1 milliliter is equal to 1.54 grams. This is more consistent. And then we'll just convert it into liters. A liter is 1,000 milliliters. And so let's calculate that quickly. Here, 180.18 divided by 1.54 divided by 1,000. And I get 0.117 liters. Okay, now I'm going to go with volume of O2, and I'm going to go gung-ho because you know what I'm going to do? I'm going to use the van der Waals equation for this. And so let's go for it. Van der Waals equation for this. So the van der Waals equation for a real gas is this. The pressure is corrected by this term. So it's P plus N squared A over V squared. And the volume is corrected by this term, V minus NB. And this is just equal to nRT. If A is 0, then that's just P. If B is 0, this is just V. And so A and B being 0 would be ideal gas. So let's go for this here. So how many moles do we have? Well, N is 6 moles we have. What's the pressure? Pressure is 1 bar, standard. What's A? A for O2, let's go back over here, 1.382. B is our unknown, that's what we're solving for. B for O2 is over here. B for O2 is 0.0319. All right, I'd like you to solve for B. Okay, how much time do you need to solve for B? V, excuse me. 5 minutes? I'll give you 7 minutes. Do you think that's enough time to solve for V? Okay, 7 minutes.